with increasing Reynolds number, which in other words is related to increasing fluid speed. When you have disturbances in the flow, the losses are higher. It's not just higher, the handbook data shows that the losses are substantially higher. Now, to explain those results, we propose to undertake local analysis of the flow field. So, turbulent. This was for flow through a pipe. So, there was an interesting question last time outside the class. The question was, the friction factor in laminar flow appears to be greater than the friction factor in turbulent flow. So, the answer I gave, which I thought I should repeat in the class, is that the comparison should be made at a given flow rate and therefore given Reynolds number. So, let us say you pick this Reynolds number. This is the turbulent branch, and down below would be the laminar branch. So, laminar, now that does not make it negative, that is a log scale. So, you can see that turbulent is much greater than laminar. Similarly, the drag coefficient at a given Reynolds number, that is the drag coefficient, but if you follow the laminar branch, the initial branch, the drag coefficient is much smaller. So, depending on the Reynolds number, disturbances can increase friction factor by let us say 10 times, maybe even more. So, and this friction factor is what determines pumping power. So, the increase in pumping effort can be substantial. Similarly, the force acting on the object can be substantially large. If you think of let us say a self-propelled object and it encounters drag, if it is 10 times higher, it means the fuel that you supply for propulsion is also 10 times higher, substantially higher. So, these have profound consequences in applications. So, as a first step, the data can be used straight and you can carry out control volume analysis. And the second part that we are going to indulge in is trying to understand why these trends are obtained. The physical laws in the continuum scale, we are still in the continuum scale. So, whether it is local or global, we are going to talk about mass, momentum, energy. So if you remember our earlier discussions, these physical laws were embedded in a mathematical identity called RTT. So for mass balance, we got this equation. For momentum, momentum is a vector equation. And the energy equation where energy is P over rho plus u square over 2 plus gz plus I being the internal energy. So in the previous calculations, internal energy was taken to be constant and temperature was given. In a problem where heat exchange, for example, a tube is heated. Let us say you have a tube in a solar collector and it is heated by solar energy. So temperature warms up. So this is the equation to be used, where the heating rate Q dot is given to you and you find through this equation the change in temperature. So the starting point for local analysis is once again the Reynolds transport theorem written for a control volume, except that we now shrink the control volume to a point. So if it becomes a very small control volume, then the integrand has to be constant in that control volume, and that constant has to be 0, because the integral is working out to be 0. So let's look at the mass balance equation. We convert the surface integral into a volume integral. And therefore conclude the local form of the mass balance equation is given now by a differential equation. So that rho is density at a point at a given instant of time. That makes it local information. U is velocity at a point at a given instant of time. So scalar equation. What is the physical interpretation that we have discussed many times earlier? Just tells you that inflow minus outflow, or let us say mass inflow minus mass outflow, will contribute to changes in density in the region being studied. Here the region is a point interpreted in the continuum sense. So, if the flow is steady, then del dot rho u is 0. If the flow is incompressible, then you can take rho out and write del dot u equal to 0. Like we discussed last time, this equation is in coordinate free form. If you want to apply analytical tools for solving this equation, then I think your volume is exceeding mine. What's your name? Tower. What is written? Tower. So, in the absence of any other information, I have to call him Tower. So, that is a journalistic approach to life. Just report whatever you see. So, but in our subject, we try to go a little deeper. You can't deny we are doing it. So, del dot u is 0. What did I say? Coordinate free form. If you have to use analytical tools for solving that equation, it's what that's a differential equation. Then you have to express it in a certain coordinate system, either Cartesian or cylindrical, spherical. These are coordinate systems generally we are familiar with. At least I was told that most students are familiar with the book by Kreyszig. I don't know if you do you know this book by Kreyszig? Some of you may know that book. It's a book on engineering mathematics. It by and large deals with solving differential equations. And those in particular are linear differential equations. So, that is the kind of mathematics that we will employ to some extent, a little bit of Kreyszig. So, let us say you want to write this equation in Cartesian coordinates. Then one possibility is to write it as this is the del operator, where I and j are unit vectors in x and y directions. This is a Cartesian plane. You can have Cartesian space by defining z, x, y, z, which only makes the writing part of it a little more elaborate. But life is three-dimensional, so there are times when you have to consider three-dimensionality. But to illustrate the central ideas of the subject, let us start with a 2D plane. So, this is dot product with the x and y components of velocity that we call u and v, lowercase u, lowercase v. So, that is u I plus v j, which quickly you can solve and get del u del x plus del v del y equal to 0 in compact form written as u x plus v y equal to 0, where the suffix indicates partial differentiation. So, it is just del u del x plus del v del y equal to 0. If you are working in let us say cylindrical coordinates, now 2D cylindrical coordinates are also called polar. So, this is the xy plane, the coordinates are now r and theta. Of course, you can relate r theta to x and y. R square is equal to x square plus y square. Theta is tan inverse y over x. So, you can always go from one coordinate system to another. Now, if you are going to work with polar coordinates, then you have to introduce polar components of velocity. Let us say u r is the radial velocity component and u theta is the angular velocity component, okay, or velocity component in the angular direction. Then the velocity vector u will be, you have to introduce unit vectors in r and theta direction. So, let us say this is E r and E theta. These are unit vectors in r and theta directions. So, this is E r u r plus E theta, theta I have shown as superscript, and the del operator will be then when you do the dot product, you have to recall that the derivative with respect to theta of the unit vectors. The unit vectors are constant in magnitude, but are not constant in direction. If you change theta, if you change r, there is no change in the unit vectors E r E theta. But if you change theta, the directions change. So, the derivative of E r E theta with respect to theta would be non-zero. So, specifically the derivative of E r with theta is E theta, and the derivative of E theta with theta is minus E r. So, these are calculations given at great length in this book by Kreyszig. So, when you do del dot u, this operation del del theta on E r and E theta will also have to be brought in. Now, in case of I and j, the derivatives were 0, because I and j are constant in magnitude and direction. So, in polar coordinates, you should be able to derive this result where there is an extra term 1 over r u in the radial direction, which is often called the curvature term. In the absence of curvature, that means if it's straight, then its absence of curvature, that means r goes to infinity. So, that term is 0, and you get back a form which is very similar to Cartesian, okay, with r and theta playing the roles of x and y. So, this is del dot u equal to 0 in Cartesian coordinates, where del dot u equal to 0 is the mass balance equation for incompressible flow. If the flow is compressible, then you will have the fuller form, where there is a time derivative with respect to density. It's a local description of the flow field. So, let us look at an example. Let us say I could do flow through a tube. I may also do let us say flow between parallel plates. Now, the x and y components of velocity are u and v. Okay. Now, if you say that flow is mainly in the x direction, two long plates, flow is mainly in the x direction, then it is reasonable to expect that the x component of velocity, I am thinking of the mass balance equation, which is u x plus v y equal to 0. So, to solve this problem, you have to identify the velocity components and you have to set up a coordinate system. You can set up the coordinate system any way you want. I can keep it next to the top plate, or I can keep it next to the lower surface, I can keep it along the axis. I place the coordinate system in such a way that it helps in simplifying the governing equations. So, if you have an expectation that the flow is mainly in the x direction and it is otherwise undisturbed, then nothing is happening from one location to another. So, essentially sometimes this state of flow in which nothing is happening, it is undisturbed in the unchanging in the x direction. Such a flow is said to be fully developed. So, then you can set this derivative equal to 0. Now, what do you expect the distribution of velocity to be? This distribution was not relevant in our global analysis, but now you are talking about local trends. So, what is the distribution? So, you may think we will solve for it later, but if you think about it, velocity has to be 0 at the walls, where the walls are fixed. If it is Newton's parallel plate experiment, then you would say velocity is 0 at one wall and equal to some given value at the other wall. If you have two plates, then velocity is 0 at both walls. So, just based on symmetry, you would expect the peak velocity to occur somewhere in the middle. Okay. So, you will have a bulging kind of parabolic distribution. In a tube also, at the wall velocity is 0. So, at the core velocity has to be much higher. parabolic kind of distribution that we have to obtain, but I am just talking about expectations. So, if the flow is unchanging in the x direction, the x derivative is 0, that means the first term is 0, therefore, it tells you that this derivative is 0. So, this is now a simple first order differential equation, which you can solve. So, what will be the solution of this equation? Just that v is a function of x is the solution of this equation. But you can evaluate this function at the walls. At the walls, the transverse velocity is also 0. There is no fluid being sent into the domain. So, you conclude what am I writing? So, here that function f x is the constant of integration. So, since v is equal to 0 at the wall, f x equal to 0. So, therefore, v is equal to 0 everywhere. So, in this simple example, mass balance tells you flow is going in one direction, then under fully developed flow conditions, the transverse velocity is 0. So, if it is flow through a tube, by integrating the momentum, the mass balance equation in polar coordinates, let us say it is a tube, then you can show that I think this tube is probably not an appropriate example for r theta. The tube is more like r z. So, let me write down for r z coordinates. So, here u z is independent of z, and u r is equal to 0. So, for a tube it is r z coordinates. A simple integration of the mass balance equation to show that transverse velocity is 0 and all the flow is taking place in one direction. So, when del dot u is equal to 0, it is quite common to introduce a stream function that helps you. The purpose of the stream function is just to help you visualize the flow. So, you remember the definition of a stream function. On a, what is this symbol? It's psi, psi. On a curve where psi is constant, the velocity vector is everywhere tangential to it. So, this is the velocity vector. Velocity vector is tangential to it. So, if I show you a streamline, so in that in the video that was shown, there was some flow going around the cylinder. You can think of that line, the green line, as a streamline. The flow is going along the streamline. In case of flow between parallel plates, flow is going straight, so all the streamlines are straight. In flow through a tube also, for laminar flow, all the streamlines were straight, but when it became disturbed, the streamlines started moving in time. So, the stream function is related to the velocity distribution as it's written as the derivative of the psi field will give you the velocity field. So, if you look at the change in psi, so we are talking about a streamline. So, on that streamline, the total change in psi, that is as you go from one point to another, how much is d psi? 0, because you are on the streamline. So, but psi is a function of x and y, so you can write it as the partial derivative of psi with x dx plus psi y dy, which is minus v dx plus u dy. So, dy dx on a constant psi line is equal to v over u. So, what is the conclusion? The conclusion is on the psi line, the velocity vector is tangential to it, right, because the dy dx is the slope, which is v over u. Therefore, velocity vector is tangential to a streamline. So, if I show you a streamline, then you know a flow is going to take place along the streamline. So, how is it connected to the mass balance equation, or that del dot u equal to 0? By the way, there is a profusion of terminology. The original form of the mass balance equation, which includes density, that you refer as mass balance. When you write del dot u equal to 0, it's sometimes called the continuity equation. What is continuous? It's the flow rate. Flow coming in is equal to flow going out. There is no accumulation of matter. There is no change in density. It's a continuous flow. It's called continuity equation. So, when you have del dot u, you may call it continuity or mass balance. But if the flow is compressible, then you will only have the mass balance equation, not the continuity equation. So, introducing this stream function, you see that the slope of a psi equal to constant line is v over u, and therefore, velocity vector is tangential to a curve psi equal to constant. So, if you substitute the definition of psi in the continuity equation, del dot u equal to 0, it's u x plus v y, but u is that derivative psi y and v is the derivative minus psi x. You substitute, so this is equal to psi y x minus psi x y, which is automatically 0. So, it tells you that introducing a stream function in a flow field will automatically represent incompressible flow conditions. So, if the both ways, if psi exists, flow, it represents an incompressible flow field. If it is an incompressible flow field, psi will exist. So, we associate a stream function with an incompressible flow field, because automatically it satisfies. This is an identity, so to say, in terms of psi. So, psi indicates an incompressible flow field. Because if you have a scalar function whose derivatives give you a physical quantity, that scalar function is often called a potential. So, in that respect, a stream function is a potential because its derivative gives you the velocity vector. So, in a given flow field, you will have many streamlines, not just one, right, depending on where you start. So, in that cylinder example, you saw that if you started far away from the cylinder, the streamline more or less remained straight. But if it was closer to the axis, it had to bend and go around the cylinder and go like that. Okay. So, in a flow field, depending on where you start, you will have a collection of streamlines. So, you may call this psi 1, psi 2, these are all streamlines in the flow field. Suppose you go from point A to point B, and then calculate so this is equal to integral, just writing d psi as I am sorry, this is A to B, psi x dx plus psi y dy. This is equal to integral A to B minus v dx plus u dy. Okay, so, the change in the stream function going from the first streamline to the second is minus v dx plus u dy, integrated from A to B. So, what is the physical message we get out of it? Maybe I can pick a new page. This is the u component of velocity and this is the u is the x component of velocity, v is the y component of velocity. So, those elemental lengths u dy, u and then dy, we are doing a 2D calculation. So, it is unit dimension normal to the plane of the blackboard. So, u dy is the little flow crossing a small element ds of AB in the x direction, and v dx, you can identify dx and dy. This is dy and the horizontal part of it is dx. The streamlines 1 and 2. So, u dy minus v dx is the small flow, incremental flow crossing AB over the segment ds. This is the segment ds. ds belongs to AB and it is decomposed as dx dy. So, when you integrate from A to B, it is the total flow crossing the space between streamline 1 and streamline 2. So, you can associate the stream function physically, you can associate it with the flow rate, okay, because you could probably pick 1 as a solid surface. Is a solid surface a streamline? Let us say this is a solid wall. So, velocity is 0 everywhere along this wall and there is no flow crossing this wall. Therefore, the wall is a streamline. So, this will have some value of psi, but because the flow field is defined in terms of the derivative of psi, psi can be defined up to an arbitrary value. So, you may pick the solid wall as a datum and set psi equal to 0 on it. If that is the case, then any other streamline like this will indicate the flow that is crossing or the flow that is contained between the wall and that streamline. So, you have a physical interpretation of psi as flow rate. So, we will use some of these ideas to help us interpret the flow field in our future examples. Okay, so, for mass balance, we have obtained two results. One is, if del dot u is 0, then in a fully developed flow field, the transverse velocity is 0. That was one result. Second result is that if del dot u is 0, a stream function will exist and the stream function is physically interpreted as flow rate. So, let us look at the momentum equation. remember the simplification of the first equation leading to the second. We first convert the surface integral into a volume integral and then break it up into two parts. For one part we apply the mass balance equation and set it equal to 0. You are left with the second term. This calculation we had done probably in our third lecture of the course. Do you remember this discussion? Some of you do. Others will catch up. You just check up your notes. See if you have this expression in your notes. It should be there early on, correct? So what is F? It's the sum of all external forces acting on the fluid medium. Okay? The fluid medium contained in the control volume CV. What is rho dV? It's mass, an elemental mass. And when you integrate over the control volume, it is the mass of the fluid. So what will be the rest of it? Acceleration. So in momentum equation, this part, so let's write it as vector A is the acceleration vector. The first term is just change in velocity per unit time at a point. See, now we are talking about local description of the flow field. So at a point, when you say partial derivative of u with time, it means there is no change in the x coordinate. So at a point, if there is a change in velocity, that will give rise to a component, it will have a contribution to acceleration. It's called the temporal acceleration. So naturally the second term, what would you call it? Because it involves derivatives in space, it's called spatial acceleration. So in the context of fluid flow, see, for a rigid body, rigid particles going all over the place, you can define its acceleration as change in velocity with respect to time. Okay. So in the flow context, you are not tracking particles, you have a fixed coordinate system that gives rise to a temporal contribution and a spatial contribution. Okay. So I think you can almost anticipate that the momentum equation will require a lot more discussion. So I will continue with it 2 weeks later. 2 weeks later, it's a new world. But I hope you don't forget. See, every new discussion is built on an old discussion, but if there's that much of a gap, I just hope you remember. But anyway, you have your notes and you have your textbook. So please stay in touch so that suddenly when I introduce stream function, you are not lost. Or if I say spatial acceleration, that should refer to the second term of the acceleration vector. So do well in your exams.